Hello there, this is the video for section 8.7. So in this video we're going to look at detecting residual correlation, and we're going to learn about what is called the Durbin-Watson test. So just a couple things up at the beginning. Sorry if you can hear my dog, he's barking at something upstairs. So correlation of the error terms frequently happens when the data set is in a time series. And so this is going to become important because later on in the course we're actually going to look at time series data. So in this case the data are observed over time, and models of time series may pose a serious problem because the values at time t is often indicative of the value at time t plus 1. So in other words, if it's hot today, it's probably going to be hot tomorrow, is kind of what you can think of. So what that tells us is that the value of a time series at time t is correlated with its value at time t plus 1. And so for that reason, the error term will be correlated, which is a violation of the independence of the error terms. And so this leads to the standard errors of the beta estimates that are seriously underestimated, which again can affect the inference procedures. All right, so we have two types of what we call autocorrelation. And so autocorrelation, these are the ways that things can be correlated through time. And so in positive autocorrelation, what we end up with are positive error terms that tend to be followed by a positive error term, and negative that tend to be followed by a negative. So again, it's the same idea of if it's hot today, it's probably going to be hot tomorrow. Whereas negative autocorrelation, on the other hand, is that positive error terms tend to be followed by a negative and vice versa. And we can test for different types of autocorrelation by using what is known as the Durbin-Watson test statistic. And so here is the test statistic. Notice that it is calculated in terms of the residuals. You've got those epsilon hats there. And so just a couple of comments about this. Positive autocorrelation is found more often than negative. Most regression packages will compute the Durbin-Watson statistic for you, so we're not going to calculate that by hand. Time series can exhibit more complicated autocorrelation structures. So these are just two simplistic ones. We're going to look at more when we get to time series data. Durbin-Watson's D is restricted between 0 and 4, and we're going to need this one here in a minute. If the residuals are uncorrelated, D is approximately 2, so we need this one and this one. And if the residuals are positively correlated, D is less than 2. If it's real strong, it's close to 0. And if they're negative, D is going to be greater than 2. And if it's very strong, it's approximately equal to 4. So all 4 of these I'm going to reference here in just a moment, and we'll need those. All right, so first of all, here is kind of a little box that describes the Durbin-Watson test. The first thing that I need to note with this is your textbook is incorrect. So make sure that if you're comparing this with the textbook, it is going to be slightly different. And again, the textbook is incorrect for this. So I'm just going to make a little note of that here. Book is incorrect. All right, so looking at the box, we could do a lower tail or left tail test, two tail test, or a right tail test. And so the lower tail test is used when you're looking for positive error correlation. The two tail is when you're just looking for correlation in general. And then the upper tail is used when you're looking for negative. You'll notice here is the test statistic. We're going to use what are called rejection regions for this particular test, and we'll look at an example here in a moment. But here are the different rejection regions and how we conclude the test. And we'll do some examples of these. And once you see a couple examples, it's not too bad. And then again, here are those 4 properties that I started from the previous page. All right. So let's kind of look at how we would go about this. So let's look at an example of a lower tail test. So a lower tail test attempts to prove that there is positive error correlation. So let's kind of look at a number line. We know that the test statistic is restricted between 0 and 4. And if it's approximately 2, that means there is no correlation. Now, the residuals are positively correlated if D is less than 2. So that's why when we do the lower tailed test, what we're interested in is this region right here. So this is the region that I'm interested in because that would suggest positive correlation. So the way that this test works, it sets up two different bounds. There's one that we call DL and one that we call DU. If our test statistic falls in this region right here, we fail to reject. In other words, our test statistic was too close to 2, which would suggest no correlation. If our test statistic falls in here, this is when we get to reject. In other words, our test statistic was far enough away from 2 and close to 0. And remember, when we're close to 0, we have very strong positive correlation. We're able to reject that null of no correlation. Now, if our test statistic falls somewhere in the middle, our test is inconclusive. We don't know what's going on. So this is why when you look up here at the box which summarizes the test, you'll notice there's a rejection region, a non-rejection region, and the inconclusive region. And we could do the exact same thing for the other two tests. So again, I'm going to write out my number line from 0 to 4. We know a 2 suggests no correlation. Well, in this case, we're interested in negative correlation, which occurs when the test statistic is between 2 and 4. But what the test does is it instead looks at 4 minus D. And so notice if we look at 4 minus D, what that does is it maps this over to the left-hand side of the number line. So again, we're again mapped to 0 and 4, but it maps it over to the left-hand side. So this comes over here since we're looking at 4 minus our test statistic, which is D. And again, we have that same idea with the lower and the upper, where we don't know what happens in the middle. If we're in here, we're going to fail to reject because we're too close to 2. And if we're in here, we're close enough to 0, so we are going to reject. So that is why when you look at the upper tail test, or the test for negative correlation, you'll notice it is in terms of 4 minus D. And then the two-tailed test, again, what it does, if we draw our number line, we've got 4, 2, and 0. What it does is it looks at equal distance from 0 to 4, or from 0 and from 4, and creates the bounds this way. And if you fall into either of these regions, you're going to reject. And the distance of each of these regions is equal. And so this is why when we look up here, you're going to notice that the rejection region and non-rejection region are both in terms of D and 4 minus D, because we're going to do one of these for if D is less than 2 or D is greater than 2. All right, so we're going to work an example here. So the first one says, find the values of DL and DU when n is equal to 30, k is equal to 3, and alpha is equal to 0.05. And we're going to perform the test for positive autocorrelation. Remember, if we're looking at positive autocorrelation, that is a lower tail test. And we're going to see what happens if D is equal to 1.3. So in order to do this, we're going to need a Durbin-Watson or a table for the Durbin-Watson test statistic to get these lower and upper bounds. All right, so I've got a copy of the table here. Now this is a table that I pulled offline. You'll have a different version of it in your book. It doesn't really matter which version you use. But a couple things to note about the table. Some tables will use a delta instead of the K. If they do, be careful with this. For this particular table, we've got that delta is equal to k plus 1. And then also the tables up at the top should tell you the level of significance. So this page of the table is a 1%. I'll turn a couple pages and you'll notice here is a 5% table. So for our particular example, we do want alpha equal to 0.05, so I'm going to use the 5% table, and notice that RK is equal to 3, so I'm going to want these columns. And then also notice that Rn is equal to 30, which is right here. So if we see where those match up, that's going to give me my lower and my upper limit. So notice for this example, my lower limit is equal to 1.21, and my upper limit is equal to 1.65. And then further, notice that our D, or our test statistic we found, 1.3, sits in between the two. So in this case, the test is inconclusive. And this is a little bit different than tests you've seen in the past, because most tests, is able to tell you reject or fail to reject. There are tests like this one where there's a middle region, which is it's inconclusive. All right, let's do another one. Find the values of D and L when n is equal to 20, k is equal to 2, and alpha is equal to 0.1 rather, and D is 3.8. So for this one, we're going to want the table that has the 1% significance level. Also, notice here that this is a test for autocorrelation. So since this is an autocorrelation test, I actually just misspoke a second ago. I need to correct that, because notice this is a test for autocorrelation, so it is a two-tailed test. So since it's a two-tailed test, we're actually going to use alpha divided by 2, which is going to be 0.1 divided by 2, which is 0.05. So I misspoke. We don't want the 1% significance, which 0.1 wouldn't be 1% anyways. We want the 5% significance. All right, and so again, we're going to look up these values. So in this particular case, k is equal to 2, so this time we're going to want this column, because remember this is going to be k plus 1. N is equal to 20, so we're going to be looking at this row. So this is going to give us these values right here. So DL is equal to 1.10 and DU is equal to 1.54. Now we want to be careful here, because notice that D is equal to 3.8. So if we go to the summary of the test, notice when we've got the two-tailed test, if D is greater than 2, we're actually going to work with 4 minus D. So notice that 4 minus D is equal to 4 minus 3.8, which is equal to 0.20. And then notice that 4 minus D, the 2.0, is less than or equal to the lower bound of 1.1. So in this case, we are going to reject the null. And so what that tells us is we are able to prove that there is autocorrelation between the two. And looking at our test statistic, that would suggest a negative correlation between the two. All right, so let's look at an example with some data. So here we've got some time series data, which gives the sale for 35-year history of a company. And we're going to consider using a first order linear model to model the sales. And we're going to do a test to determine whether the regression errors are positively correlated using alpha equals 0.05. So under the null hypothesis, we're going to make the assumption of no error correlation. And under the alternative, notice we're trying to prove if they are positively correlated. So under the alternative, we are going to have positive error correlation. So notice this is going to be a one-tailed test. So the next thing we need to do is figure out what our test statistic is equal to. Remember, the test statistic is going to be that D. So what we're going to do is we're going to look at several different pieces of output here. So here we have the output for SAS, and you'll notice I've already got the Durbin-Watson highlighted for us, so we know that D is equal to 0.82. Looking at the rest of the output, you'll notice that we've got output for the rest of the observations, as well as some of those diagnostics that we saw earlier. So this is from SAS, but you could also do this in Minitab, or you could do this in R. And notice up here at the top is where you have the SAS code to get this. We've just added in that DW. That's what's adding in and getting you that D test statistic. Right. So here D is equal to 0.821. K is going to be, that's our number of predictors. So in this case, K is just equal to 1. Alpha is equal to 0.05. N is the number of observations, which is 35 for this example. So again, we're going to go to our table. Alpha is 0.05, so again, I'm going to use that 5% table. This time N is equal to 35, so I'm going to need this row. And then K is equal to 1, so I will need this column. So here are my endpoints. So notice my lower bound is equal to 1.40 and my upper bound is equal to 1.52. Notice that my D falls below the lower bound, so we are going to be able to reject in this case. So at the 5% significance level, sorry if you can hear my dog squeaking his dog toy in the background, we have enough evidence to conclude that the errors are positively correlated. And remember, the whole reason that we perform this test is that is a violation of one of our assumptions, and we need to always check to see if we have violated any of our assumptions. So this video is going to end the section 8.7 video, or 8.7 notes rather.